Okay, so now that we've learned some basics about hypothesis testing, we've done hypothesis testing for proportion, the next thing is to talk about hypothesis testing as it relates to the mean. So this is pretty important thing for us to learn, as well as what we learned last week with proportion. There's two ways to really do this, but we're going to only focus on the more realistic way of doing it, which is that we're going to assume that we do not know the standard deviation of the population. And therefore, we will be using t-distributions, not z-distributions. So t-scores, not z-scores. So a couple of things here with our notation. We know n is sample size, x bar sample mean, s is the sample standard deviation, and we'll use this mu sub x bar as our population mean. We usually just use mu, but sometimes the textbook also switches it and it is mu dot x bar. All right. So hypothesis testing regarding the population mean. What do we need? Okay. What we need to do this is that we need a sample to be a simple random sample. We need a good sample. This is always the case. Second, the sample has no outliers and the population from which the sample is drawn is normally distributed, right? But sometimes you don't know that. So the next thing is we could also deal with a sample size that is bigger than 30. So if we have a small sample size, we need some information. If we have a sample size that's bigger than or equal to 30, then we don't need that information. So no outliers and normal distribution, or sample size is bigger than or equal to 30, right? And the last thing is that the sample values are all independent. All the ones we're going to do, they're going to have all these things taken care of so that we can do it. But if you were working in the real world, these would be some of the things you would look for to be able to use your t-distribution. So our test statistic will be a t-score. This is the formula for our t-score, x bar minus the mean divided by s over the square root of n. We already talked about how to calculate that when we did our basics. And again, we're going to use the student t-distribution, and minus 1 would be our degrees of freedom in our t-distribution. When we're dealing with t-scores, the critical value method is actually going to be easier for us to do as opposed to the p-value method, but we could do both. I'll show you how to do both and why p-value method is problematic and some ways around that. But for us, the critical value method is the better way to go. When we use z-scores, it didn't really matter, but for t-scores, it's easier to read our t-score chart in one direction, which is why the critical value method is better. So let's look at this. So the author of the book obtained times of sleep for randomly selected adult subjects included in the National Health and Nutrition Examination Study. Those times in hours are listed here. So 4 hours, 8 hours, 4 hours, 4 hours, 8 hours, etc. Okay? So the unrounded statistics from this sample would be the sample size is 12, the sample mean is 6.8333333, and the sample standard deviation is 1.99240,984. Again, you could find the mean from this sample, the standard deviation from this sample using the formulas we've learned in this semester. So a common recommendation is that adults should sleep between 7 and 9 hours. Use a 0.05 significance level to test the claim that the mean amount of sleep for adults is less than 7 hours. All right? So what do we need here? What we need first is the original claim. The original claim is that the mean is less than 7 hours. Okay? And we know our sample size is 12. Our sample mean, we'll round this to 6.833. And our sample standard deviation will round to 1.992. Less rounding would be better, but 3 decimal places should be good. What else do we need? We need to do the opposite. So the mean is greater than or equal to 7 hours. 7 hours. Okay? Then our H1 and our H sub 0. H1 is that the mean is less than 7 hours. Why? Because this one here does not contain an equality. That's the original claim. Okay? And then the mean equals 7 hours. is our h sub 0 because it's always equal. Now, this tells me I have a left-tailed test because of this symbol right here. So all that we can get pretty easily. All right, next thing we want to do is calculate the test statistic. Once we do that, we're going to choose the critical value method because that's easier, and we're going to get to our final answer. So the next thing we want to do is calculate the test statistic. So in that, we have the t-score, and we should do x bar minus the mean over s over the square root of n. So we fill all that in. X bar was 6.833. We used the claimed value of 7 as our mean from our population. S was 1.992, and the sample size was 12. Make sure you calculate this denominator and this numerator separately. We've talked about this. Then do the division. That way you don't mess up with your calculation. So when I do this calculation, I got negative 2.90. Okay, there's my t-score. So then what I'm going to do is I'm going to do the critical value method. So I'm going to say I have a bell-shaped distribution. This is a t-distribution. I'm going to do the critical value method. Remember, it's a left-tailed test. In the critical value method, this is the critical region. This right here is your critical value. The area is your alpha. In this case, we wanted a 0.05 significance level. And so in the 0.05 significance level, we want to figure out what this critical value t-score is. And then we're going to decide if this test statistic is in or out of the critical region. Well, remember, our sample size was 12, so our degrees of freedom is 11. So we go down degrees of freedom of 11, okay? And now our area in one tail is 0.05. So you match that up, and here is your critical value. So in this case, since it's down here, we'll make it negative 1.796. And then the question is this t-score in the critical region? Remember, zeros here being negative 2.90. Yes, the t-score, this test statistic, is in the critical region based off of this number here. This would be to the left of that number. So once we know that the test statistic is in the critical region, we can finish this off. So if the test statistic is in the critical region, we're going to reject h sub 0. Then we go through our final steps. Does the original claim contain the condition of equality? No, the mean was less than 7 was our original claim. No equality there. Okay? So then, did we reject h sub 0? Yes, we rejected h sub 0. So here's our final answer. Okay? The sample data supports the claim that the average sleep time is less than 7 hours. Okay? The sample data supports the claim that the average sleep time is less than 7 hours. So there you go. Okay? We got a good answer out of that because we got something that actually made sense. In that we got a clear-cut answer. And doing it with t-scores really is not that much different than doing it with z-scores. All right. Now that was a critical value method. I like that method better for t-scores, but I want to show you how to do it with p-value method, and you see that you could still get the same answer. Okay? But it's a little bit trickier. So let's draw the same picture, but in this case now, this left-tailed test is going to be the p-value method. So this will be the p-value, which we need to find, and this number right here is going to be the test statistic. Okay? The test statistic, remember, was negative 2.90. That was our t-score. Okay? So we want to figure out what this area to the left is. Well, here's what we have to do. We're really going to have to estimate it. And then what we do is we compare the p-value to alpha. Okay? Alpha in this case, remember, is 0.05. So we want to look at these two and figure out what the comparison is, which one's bigger. All right, well, our degrees of freedom was 11, so we know that. So we're working with this row right here. Let's highlight it. This row right here is the row we're working with. And what we need to do is figure out what this area is. Well, what we need to do is we need to say, where would this t-score fall in this row? Now remember, it's negative 2.90, so you would have to sort of look at this as a bunch of negative values. So negative 2.90 would actually fall, if you think of all these being negative, it would fall right here, okay? Here's 2.7, here's 3.1, so 2.9 or negative 2.9 would fall in here. All right, so then we look at this and go, all right, well, it's between here. It's less than this one and bigger than this one. So what we can say about our p-value is we don't know the exact value, but the p-value is greater than 0.005, but less than 0.01. So that's the p-value. It's between those two values because our t-score that would give us the p-value, or the area and one-tail, would have to be between these two t-scores, so the area and one-tail would be between these two areas. That's the best we can do when we read the t-score chart backwards, which is slightly problematic. However, even if we don't know the exact p-value, but we know for sure it's between these two values, can we say that the p-value is less than alpha still? Okay? And yes, we can, because we know alpha is 0.05, and we know the p-value ranges between these two values, which no matter what is still going to be less than alpha. So we can say that the p-value is less than alpha, and when we do the p-value method, when the p-value is less than alpha, we reject h sub 0. So we can still get to that point, it's just a little bit trickier. Okay? Now there's one more way to calculate the p-value without using this table, and that's to use an online calculator. So if you use an online calculator, what you can do is you can plug in your test statistic and it'll tell you your p-value right away. So with this website, it's very simple. You put in your t-score, you put in your degrees of freedom. You should also put in your significance level and whether you have a one-tailed or two-tailed test. I put all that in, I hit calculate, and what happens is it tells me the exact p-value as well as the fact that the p-value is less than the significance level, is less than alpha. So this is how I can get the exact p-value. Again, it's using all the same stuff that we've learned before, really, which is using calculus to get this answer, but rather than using a sort of a table that is limited, it's doing the calculus for you and getting you the exact p-value. Either way, you still get the same answer, but you know, it helps to get that exact p-value using this simple p-value calculator. And I have this linked in our Blackboard course. Here's another one. So statistics students believe that the mean score on the first statistics test is 65. The statistics instructor thinks the mean score is higher than a 65. He samples 10 statistics students and obtains a score, the following scores of 65, 65, 70, 67, 66, 63, 63, 68, 72, and 71. So that's your sample of 10 students. He performs a hypothesis test using a 5% significance level, so 0.05 alpha. The data are assumed to be from a normal distribution. All right, so what do we have here? Well, let's look at this. We're going to do the hypothesis test from the instructor, okay? The student thinks it's a 65, the instructor thinks it's a higher than 65. So we'll go with the hypothesis test of the instructor, and we're going to say that the original claim is that the mean is greater than a 65, okay? Now, as far as our sample information, we know our sample size is 10. What we don't know is the sample mean or the sample standard deviation. We would have to actually calculate that using all these data values. Well, the good news is I already did that for you. So 67 is our mean, and our standard deviation is 3.197. Okay? Our alpha is 0.05, and we have everything we need to get going. So what we're going to do is we're going to write the opposite, okay? The mean is less than or equal to, the mean is less than or equal to 65 is the opposite. So then H1 is that the mean is greater than 65. Why? Because that's the one that does not contain inequality. H sub 0 is that the mean equals 65 because H sub 0 is always equal to the claim value. This tells us we have a right-tailed test. Okay, right-tailed test. All right, we have everything we need to get started here. Next, we need test statistic. The test statistic is going to be a t-score. We use x bar minus the mean over s over the square root of n to do that. In this case, x bar was 67. The mean from the population, we'll use the claim value of 65. S is 3.197, and the sample size is 10, so the square root of 10. So there you go. Put that in your calculator, and you will get a t-score of 1.98. Okay? So there is your t-score. Okay? That's your test statistic. So then what we're going to do is we're going to go on to the critical value method. Okay? I'm not even going to bother with the p-value method since the critical value method is the best way to go here. So in the critical value method, what we're going to do is we're going to say, all right, here is our t-distribution. We had a right-tailed test. This is our critical region. This is our critical value. What we need to do is we need to look at this critical region and say, okay, this is our alpha, which was 0.05. So our area in one tail is 0.05. Our degrees of freedom is 9. And we need to then find the critical value here. Once we do that, we figure out where that test statistic is going to fall. Remember, the test statistic was 1.98. And does that critical value of 1.98 fall in or out of this critical region? If it's in, we reject. If it's out, we fail to reject. So let's look at our t-table. So our area in one tail was 0.05. Our degrees of freedom was 9. So we look at this, and there is our critical value. So we go back to our picture. Our critical value here is 1.833. This is our alpha of 0.05. Our test statistic was 1.98. 1.98 would be in here. 1.98 would be to the right of this value. Remember, 0 in the middle. So our test statistic is in the critical region. So we will reject H sub 0. Again, right here, test statistic is in the critical region. We reject H sub 0. So if we follow our answers, does the original claim contain inequality? No. The mean was greater than 65 was the claim. So no. Did we reject H sub 0? Yes, we did. Where do we end up? This box. Again, the sample data supports the claim. The sample data supports the claim that the mean is greater than 65. Okay? So our mean is greater than 65 is going to be supported by our sample information. The sample mean was 67. Is that greater than 65? Yeah, it's greater than 65. Is it big enough that we can support this claim? At first, I would say I'm not sure. That's pretty close. But based off our sample information, the sample data will support this claim. Okay? So we can say that the average score is greater than 65 based off of our sample information. So you see that hypothesis test, again, not that complicated now that we've been doing it for 3 weeks. You should be able to follow those steps in the critical value method to get to your final answer fairly easily. And so all of them are going to follow the same pattern. Okay?